well, another digression is that my career was that I sort of as a hobby, I'd started constructing fractal landscapes. I got interested in the idea that if you just have some this idea of Mandelbrot that that you have a a sort of scale invariant fluctuation is producing the terrains that we observe, and so people construct these very crude models of how this might work, but I came up with some ideas about how to do this in a less artificial way, and wrote computer programs to initially on the Amiga computer, which was my home computer at that time, which you could construct fractal landscapes, by and make pictures of them. So and that eventually wound up by late 90s and early 2000s with actually a former postdoc at Mandelbrot said, actually was writing a commercial program to construct fractal landscapes, and I contributed something to that. My contribution was a way of, so you can construct landscapes, but if you just do sort of random fractal landscapes, you end up with things with basins as well as as mountains and things which don't really look at all like any landscape and actual landscape in the earth. So I came up with a way of creating random river networks as part of this, and so you lay down springs and the rivers flow from the springs, and they constrain as you go to finer and finer scales, how the terrain around the rivers is to produce valleys and so on. So anyway, so I got sort of much more involved with that than I really should have, and this program eventually came out, but was never a commercial success. But then, I was also interested, in ways of doing numerical relativity and perhaps a little better looking at ways of considering in terms of being able to calculate, for instance, radiation from colliding black holes or something like that. The idea of doing the calculation on hypersurfaces which are asymptotically, because then you can, if you just consider some ordinary sort of constant time hypersurfaces, that the problem is, of course, that the radiation as it goes out, you have to keep solving for a very long time to see what the real asymptotic properties of the radiation are. But with these asymptotically null hypersurfaces, or hyperbolic hypersurface, that they sort of follow the radiation out, so you don't need. But there's some interesting issues, or how you handle this in a good way. And though I have to say it never really went anywhere in terms of pushed by the mid-2000s, well, the early 2000s, mid-2000s, the industry of calculating radiation from black holes thrown together was in full swing, and they had their own ways of doing things, which weren't terribly interested in trying to do something completely different. So, and we're able to, come up with pretty good ways of doing things. So in 2005, I started. Well, I had some macular degeneration in my eyes for a while, but then suddenly I developed it's called wet macular degeneration. You get a blister on the retina in my left eye, and had to have an operation, which was not successful in terms of retaining the core central vision in my left eye. So anyway, at that point I decided to retire, and retired in 2006. So the next big change in my interests came when this whole idea of firewalls in connection with black holes. The idea that if you say that you want to preserve unitarity, and the late Hawking radiation has to be entangled with the early Hawking radiation, so you end up with a pure state outside, the black hole. That as the black hole evaporates, then that there's a conflict between regularity on the event horizon, because according to quantum theory, you can't have, if you have two quanta entangled with each other, they can't be entangled with the third quantum. So you can't have the Hawking partner of the late radiation. If the Hawking particle is entangled with some earlier Hawking particle, there can't be a partner entangled with that Hawking partner inside the black hole. And that leads to, it was argued, would lead to a singularity on the horizon with some huge energy propagating along the horizon. No, I thought that was a ridiculous picture. What I find, though, unfortunate is that you have all these different schools, well, loop power gravity in particular, versus the string theorists, who have completely different pictures of what's going on, and don't really talk to each other to try very much to try to resolve the conflicts. And there was some attempt to bring both string theorists and loop power gravity people together last summer at the Perimeter Institute. They had a quantum gravity conference, which tried to do that, but I'm not sure how successful it was. But so anyway, so I'm in my dotage. That's what I've been doing. But as I said, for a very long time, I hadn't really paid much attention to all these issues regarding unitarity and so on. But once people started talking about firewalls, I figured I should try to do something. Though I don't find, unfortunately, what I really know how to do is classical general relativity. So I'm not an expert at all in quantum gravity of any kind. Difficulty is that these sorts of models do not have Cauchy hypersurfaces. I mean, the resolution of the singularity is there's resolution of the singularity, but you end up with, as you continue, do the continuation of the geometry, you end up with a new astronomically flat region, basically, whose past, as you try to then extrapolate to the past from that, you do not intersect the original hypersurface before the formation of the black hole. So, it doesn't resolve, well, if you want to resolve the unitarity problem in a way consistent, say, with ADS-CFT, so you're saying that it really is a single asymptotic region at large radii, and things should be causal and unitary within that one region, then that's not the case, for these models. So now, of course, you could take Bob Wald's position is that, well, maybe things shouldn't necessarily be unitary, and that's fine too. And this whole question of ADS-CFT is interesting because, so I'm not really sure how much ADS-CFT really explains about our universe, because it's universe. And while, there are some theories of quantum gravity which, correspond to the CFT, the bulk theories of gravity, which have the CFT correspondence, and therefore are explicitly unitary. Then, the question is, are those relevant? Are those the correct theories of quantum gravity? And I'm very agnostic on that. I mean, I have no idea. But actually, at that time, I wasn't at all sure that we would ever be able to actually see the shadow. So the way that was done, in the proceedings of the Slesouche Summer School, and basically as an exercise for how to deal with null geodesics in the Kerr metric. So it was not intended as some real prediction. I mean, I just did the extreme Kerr black hole, for instance, and so it was just sort of an exercise in using considering non-zero angular momentum geodesics in Kerr. But of course, it is very exciting now that we actually see the shadow, and but I think in a way too much is made of that paper because, again, now at the same time, my first graduate student at the University of Washington, his thesis was not on the shadow per se, but on, you imagine a sort of a point source of radiation like a star orbiting a black hole. Then you see multiple images, right, if it's close to the black hole. And so he did a thesis on calculating, how the brightness of calculating these images and how the brightness varies as the star orbits around. And of course, so that's also involves solving non-radial, non-zero incrementum geodesics. And, so it's definitely more complicated than just calculating the shape of the shadow, but it's also relevant to perhaps to interpreting these current observations what you see is not, in terms of brightness, is things that are the propagation of the radio. What you see is this bright ring is strongly, of course, depends on the propagation through this highly curved geometry near the horizon. But I'm not sure I deserve much credit for that first paper. Well, it was wonderful to see the picture, and it's, again, there are these people who try to argue there really isn't a black hole. You have some graphite star or something, and then, which in some cases, in a lot of cases, you still expect to see a shadow, but so I wouldn't say seeing the shadow is any definitive proof that those ideas are correct, but still, I have a pretty strong belief that general relativity really does work at the horizon of a large black hole, and that I would be astonished if there were any evidence to the contrary that comes out of. But it's really exciting to actually have some evidence as opposed to just theoretical presumption. And prospects of getting more detailed information. It's quite interesting. So yeah, it's as an experimental, observational achievement, it's amazing they were able to do it. Well, I would say that teaching has been one of my weak points. One thing I did inherit from my father was being somewhat uncomfortable, shall we say, giving lectures and things like that. And I wouldn't say I mean, compared to, certainly to anybody like, say, Kip Thorne, who has a huge array of graduate students and very talented people. That's not so much in my case. So I tended to work sort of not necessarily alone, but more sort of by myself rather than being sort of actively collaborating with students that much. I mean, or some to some extent, but not the extent that's. I don't know. I mean, I guess to follow your interests, I mean, it's hard to predict what's going to happen in the next 20 years, say, in science to be, whether we've had an amazing run of developments in cosmology and relativistic astrophysics and so on, which are still continuing, but it's a little hard to see how they will continue at the same pace that they have been in the last 50 years or something, last 60 years. What's happened is that you have these large collaborations now, which seem to dominate things very much, and I was never really part of some big collaboration. So you have LIGO, and you have, it's just an enormous industry. And there are still some very interesting developments in astrophysics, and like these fast radio bursts I find fascinating. Both in what they are in their own right, but also how they can be used as cosmological probes. So it's hard to say, how long this huge surge we had in science is going to last, or whether it will last, I think, in the same way. It's certainly discouraging here in the U.S. in terms of the people running the government seem to have no interest, be anti-science more than pro-science. So I feel very fortunate to the way things went during my career. But whether in the next 50 years will be as fortunate as I'm not too terribly confident. But we'll have to wait and see, I guess. Or I won't be around that long. But yeah, I don't know. I mean, I'm somewhat discouraged about just the way things are going in the world generally today, and it's not only the U.S. but in other countries too. So I'm certainly. So it's been a great time to be a scientist, particularly in the fields I've been in the last during my career. But question is how well it would be sustained, and it's hard to say. So and then there are some of these questions like having to do with unitarity, the connection with the fundamental properties of quantum theory in space-time. How whether they're very deep questions, but it's a little hard to see how we'll ever get any real experimental confirmation of a lot of these things. And so the question is, will people still be arguing about black hole entropy in another 50 years? I don't know.